Good morning. So, past time we concluded the following. Not enough to deal with strengths only, so we can actually add that not enough to deal with stiffness also. Buckling is an important consideration. So until now we talked about three failure mode: strength, stiffness, and buckling. So I will consider some examples. So this is lecture 17. So look please. This is example 13.2 from the book. The W6 times 15 steel column is 24 feet long, 12 and 12 here, and is fixed at both ends. Fixed means clamped. Now, shown, and it is shown in this figure 13.11a. The load carrying capacity is increased by bracing it about the YY. So look please, that is YY, that is X-axis. And along YY weaker axis, so it is braced. Why we would do bracing? Because if we don't do the bracing, or if we do not need this additional support, as it were, then column will buckle in the weaker direction. Because buckling load is, we remember buckling load expression. Buckling load expression is so 17.1b, that is 17.1a. P critical equals pi square EI over L square. But if we talk about two directions, let us say, two directions, then there is this one. So then there is moment of inertia with respect to this axis. So moment of inertia with respect to this axis is maximum, and moment of inertia with this axis is minimum out of two. Okay? So that is in this case, but actually I should have made a different picture. I should have made a picture like this. So then that is I max and that is I mean. So likewise, when we have I beam, so then there is this I max, that is here, and that is I mean. So if we don't do the bracing, then there will be buckling in YY direction, so we are doing this brace. So how do we do the bracing? We are using some struts, okay, that are assumed to be pin connected. So these are pin connected. So this is clamped. And this is also clamped. Okay, here there is simple support. Determine the load it can support, means this system, this column can support, so that the column does not buckle, nor the material exceeds the yield stress. So look please, it does not buckle, and nor the material exceed yield stress means that is strength requirement. So there are two failure modes. So I will show you again this problem. That is a problem. So it says, take please E steel modulus of elasticity 29 times 10 in power 3 KSI, and sigma y, that is yield stress, 60 KSI. Okay? So I will show you this. I hope that you wrote this. By the way, I have an announcement that, you see, I intend, as before, to scan the material and place the lecture notes on Canvas. There is a matter that we have new copiers, and I don't know how to scan. And one professor yesterday complained that he was unable to scan. So I very much hope that I will be able to scan. So that is a picture. That is the x-axis. Okay? That is y-axis. The buckling behavior of column will be different about x-axis and y-axis due to bracing. The buckled shape for each of these cases is shown here. So I will show you here. That is 11, so that is this one. So that is clamped case. Okay? And that means that effective length is 12. Do you remember we showed that effective coefficient for clamped column is 1/2. Now, second, in the other direction where the bracing occurs, this we said bracing makes simple support. So here below will be clamped, and here will be simply support. So then it is 0.7, okay? Okay. So let us come back. Effective length for the buckling about x-axis is KL in x direction, because half of 24 feet will be 12 feet, and that equals 144 inches, because feet contains 12 inches. Okay? Please repeat this KL business. I am not starting a lecture with new material, absolutely new material. I am relying on previous material. In order to understand this material, we have to know the previous material that was covered in the previous lecture. And I cannot repeat this material again and again and again. So, about the y-axis, KLY equals 0.7 of 24 feet. Okay? And equals 8 for 0 feet, or times 12 equals 100.8 inches. The moments of inertia are found from the table in Appendix B. Okay, we have Ix equals 29.1 inch in force power. Iy equals 932 inch in force power. Now we are using formula of buckling load. P critical with respect to x-axis will be pi square EIX over KLX squared. So we calculated this was 144 inches. So this here we will have 144 inches squared. Here pi squared, 20, that is moment of inertia. Sorry, elastic modulus, 29 times 10 in power 3 KSI, that is E. And then Ix equals 29.1 inch in force power, will be 4017 kips. Now in y direction, pi square EIY KLY square will be pi square. Then E is the same, 29 times 10 in power 3 KSI. Now moment of inertia equals 9.32 inch in force power. Divided by 100, we calculated KL was 100.8 inches. This value squared. So this gives me 262.5. So even so we did bracing, still this buckling load is smaller than previous in x direction. By comparison, we conclude buckling will occur about y axis. So if buckling occurs, then occurs within y axis. The area of the cross section is, from the table, 4.43 inch squared. So average compressive stress will be sigma critical divided by A equals this one. So it is, we calculate with respect to smallest buckling load, 262.5 divided by 443 inch squared. So we get 59.3 KSI. So that is a stress that will be incurred. This stress is less than yield stress. Okay, yield stress is 60 KSI. So 59.3 is less than 60. Since this stress is less, than yield stress, buckling will occur before the material yields. Okay, so buckling is more dangerous failure criterion than strength, than yielding. Thus, then, P critical equals, so we calculate, so the critical value equals 262.5, or he approximated 263 kips. Note, okay, so that is what we were asked. Determine the load it can support. So the system can support this load. Okay, from 13.12, it can be seen that buckling will always occur about the column axis, having largest slenderness ratio. Since a large slenderness ratio, because slenderness ratio is in denominator. Since a large slenderness ratio will give a small critical stress. Thus, using the data from radius of gyration from the same table, radius of gyration equals 256. KL we calculated in x direction is 144. So here is 56.2 is the slenderness ratio. In y direction, slenderness ratio is 100. KL we calculated as equals 100. Okay, 100.8, that is here. Okay, here was 144, 100.8, divided by radius of gyration in y direction equals 1/46 inch, so it is 69. Hence, y-axis buckling will occur, which is the same conclusion reached by comparing 1 and 2. Any questions? Please, if you have any questions, please send me by electronic mail, and I will try to answer to everyone. If you paid an attention, yesterday I got 3 questions, and I answered separately to these 3 questions in emails. So pay attention here in this problem. Two failure criteria are dancing in the discotheque. These criteria don't know anything about coronavirus, probably. Second example. Second example is like this. Okay, first of all, I will read the problem. So that is example 13.3 from our book. And book is freely available on the web. Now it's an aluminum column, is braced on the top by the cables so as to prevent movement at the top along the x-axis. You see, that is this x-axis. That is this x-axis. Why don't you make a picture? That is x-axis, and that is y-axis. Here they prevent with the x-axis. If it is assumed to be fixed at the base, that is clamped. Determine the largest allowable load that can be applied. So largest load that can be applied to this system. Now in this problem, there is a difference between this problem and previous problem. Use a factor of safety. For buckling, Fs equals 3. So we will write down that in previous problem, we did not have factor of safety. So previous problem in this sense was less realistic, because every time that you are designing as an engineer in your firm, you will have factor of safety. There is a code, and code says factor of safety. European code says or factor of safety or level of reliability. Anyways, you have to follow the code. So this problem is more realistic because there is a factor of safety for buckling, which is 3. Pay attention, 3 is not a small number. And I will tell you a story that I wrote a book Factor of Safety and Reliability. Friends or foes. So that is Kluwer, Academic Publishers. So I told one faculty member I was writing this book. He said, your book will be very short, like factor of safety equals 3, or maybe like factor of safety equals 2.3. So that is what his comment was. Okay, my book was longer than this, several hundred pages, but interestingly, a factor of safety was introduced apparently for the first time. By French engineer Belidor. I think in year 1723. And he was designing a church in Paris and used factor of safety equals 2.3. So exactly the same, one of the numbers that Professor in FAU used. So first time Belidor in 1723 said, let us use factor of safety. And he said it equals 2.3. So if you are dealing with factors of safety and their connection with reliability of structures, you can get this book and read when you will be working in industry. Let us come back. So now look, please. Buckling with respect to y-axis, okay? So pay attention. This beam or this bar can move along this. There is this cable. So it can move in this direction along this cable. So that will be the buckling mechanism. So that means that effective length is twice this length. Where is this length? So let us have a look here. Yeah, 5 meters. Okay? Oh. Where does it say length here? Okay, anyways, length equals 5 meters. Yeah. So that means that effective length, because it's clamped free, equals 10 meters. Okay, L effective equals 2 times L equals 10 meters. Okay, that is XX button. K equals 2, so that KLX equals 2 times 5. And equals 10 meters. For YY axis buckling, K equals 0.7. So KLY equals 0.7 times 5 equals 3.5 meters. So then we get, please, the following buckling loads. Pi square EIX KLX squared. So material E of aluminum, modulus of elasticity of aluminum equals 70 gigapascal. In previous problem, we dealt with English units. Here we deal with SI units. That is what is customary in modern books. They are giving some examples in English units, and some other examples in SI units. So sigma y equals 215 megapascal. Cross-sectional area 7.5 10 in minus 3 meters squared. Ix equals 61.3 10 in minus 6 meter in force power. Iy equals 23.2 10 in minus 6 meter in force power. So P critical x equals pi square EIX over KLX squared equals pi square 70. So we have gigapascals, 10 in power 9 Newton over meter squared. Then I have to multiply by Ix, 61.3, 10 in minus 6 meter in force power. Here KLX equals 2 times 5 equals 10 meters squared. This gives me 424 kilonewtons. So P critical in y direction will be pi squared EIY KLY squared. Pi squared 70 10 in power 9 Newton over meter squared multiplied by IY 23.2 10 in minus 6 meter in force power. KL equals 3.5 meters. So that is squared. So then we get 1.3 meganewtons. Okay? So allowable stress, okay, by comparison, P is increased by column, as P is increased, the column will buckle about the x-axis. Okay, this is smaller than this. So P allowable then equals P critical divided by factor of safety. 424 divided by 3 equals 141 kilonewtons. So let us calculate now critical stress. Critical stress equals P critical over area, 424, divided by area, 7.5 10 in minus 3. Okay, that is here, 7.5 10 in minus 3. Equals 56.5 megapascals, which is less than yield stress, 215 megapascal. So Euler's equation can be applied. Why? Because we used, why this comparison? Why this statement? This statement is made because Euler's formula is applicable for elastic range. So just to remind you, (17.1). So this is 17.2. So just 17.3. If you forgot, if someone asks, what does it mean? Applicable in elastic range. So the answer is as follows. Let us look at sigma epsilon, stress stress-strain diagram. So that is sigma, that is epsilon. So that is this diagram. Okay, so strength is this epsilon is delta L divided by original length of the specimen, which is subjected to some load or stress. Okay, until here, there is this is proportionality limit. So that means that until sigma smaller or equal sigma proportionality, there is proportional connection between sigma and epsilon. Okay? So actually that is how Thomas Young, contemporary of Sir Isaac Newton, stated, deformations as stresses. But he wanted to keep this as a secret. I mean, he wanted to keep this law as a secret. So he used an anagram in Latin. I will not write this in Latin, what he did, but I will just take deformations. Yes? So he wrote, let us see. As deformations. Then he wrote, as stresses something like that. So he wrote this ADES, SFT, or then people had to decipher. Unfortunately, do you remember I told you a story about Hippasus, who was thrown overboard by Pythagoras, by Pythagoras' order. He, Thomas Young, refuted once Newton, who was a president of the Royal Society. So Newton ordered, they were not on the ship, so Newton did not order Thomas Young to be thrown overboard, but Newton ordered Young's portraits in the Royal Society to be placed in fire. That is what is happening. Sometimes even scientists behave very, very, very badly. So now, elastic range means, pay attention. Beyond this, this is a straight line. So here, the line is straight. So sigma is proportional to epsilon. How to make equal? So there is some coefficient, E epsilon. So that is modulus of elasticity. So this law is called Hooke's law. I mean, Thomas Young just said that sigma is proportional to epsilon. Hooke said that, okay, in order to have equality, we need some constant, and that is modulus of elasticity. Now, here still, there is some, until here, that is elasticity modulus, elasticity limit. That means that if I'm unloading, then system will go back according to that line. But if I'm unloading from here, this will not go like this, but will go like this. Okay, you know all of this. You know from strengths of materials. You know from the course about materials. So I'm not going to repeat this. But in this particular problem, we said that this value that we obtained is less than this value, which is sigma yield. And therefore, Euler's formula can be applied because Euler's, for obtaining Euler's formula, we used elastic behavior. So I will continue. Any questions? All this were related to some ideal situation. What is this? One, elastic behavior of the material. What is elastic behavior of the material? So sigma epsilon 0, so linear behavior. So sigma equals E times epsilon. Second, load is applied concentrated load. Is applied centrally. What does it mean centrally? I have a beam, let's say circular cross-section. Then load is applied in the center. However, in realistic life or in real life, we encounter non-ideal situations. Like what? So that is what happens if behavior is like this. Or non-central application of the load. And that is like this. So that is the center. But maybe by chance we wanted to apply the load. We wanted load to be here, but maybe it is applied here. So there is some distance, E, distance between center of gravity of the cross section and the point of application of the load. This distance is called eccentricity. Okay, we will deal with this issue now. Eccentric means off the center. Application of the load. Any questions? When I'm asking you, do you have any questions, I actually do not mean that suddenly I will get questions because the room is empty from the point of view of my students in the class Intermediate Strengths of Materials. But I'm stopping by because at this point, when you are reading this lecture, when you are viewing my lecture, then you might have a question. Then you may want to write this question. Yes, you cannot ask me because I'm not there, but you can write down this question. Later communicate to me by electronic mail the questions. Now, when you are asking the question, you don't have to limit yourself with one question. You can put 1, 2, 3, 4, etc. And the good thing is, if you will write on page 17.6, I have this question. On page 17.5, I have this question, etc., etc. Why? Because I will open then that page, and I will easily understand what the question is. Otherwise, if you put generic question, maybe it will take me time to understand what question pertains to. So we're talking about so-called second formula. Okay? Look, please, here there is an example of this eccentricity. It says the column supporting the crane is unusually long. It will be subjected not only to uniaxial load, but also to the bending moment because of eccentricity. To ensure it will not buckle, it should be braced at the roof as a pin connection. Okay, so that, but the main thing is that we are dealing now with non-ideal situation. That is the second formula. Not second, but second. So we will see second is a function. So second x is 1 over cosine x. So we will, so from here, this word second. So there will be something like this in our analytical derivation. This second function will be. The Euler formula was derived assuming the load is always applied through the centroid of the column's cross-sectional area and that the column is perfectly straight. This is actually quite unrealistic. What is unrealistic? Unrealistic, an assumption. That means that we dealt with something that is not realistic, not appears, since manufactured columns are never perfectly straight. So please, that is very, very important to know. I will actually write down this sentence, 17.8. Manufactured columns are never perfectly straight. So usually, realistic columns have the form of some random behavior. Okay, so I'm teaching another course, not now, but I will give you the title, Design Against Uncertainty. That is a course, okay, which uses several things, several ideas. Probabilistic methods, then or fuzzy sets, or concept of anti-optimization. That means worst case design. I'm not writing this to invite you to take my course. I'm informing you that there is a whole science behind this statement that manufactured columns are never perfectly straight. The question is how to deal with this not perfectly straight. How to deal with not perfectly straight systems. And there are many. Okay, here we will deal with one simple problem where no randomness will be used. Here we are not going to use any randomness. We just assume that there is some deviation from the regular form. nor is application of the load known with great accuracy. You see? Not known with great accuracy means there is uncertainty. You may say, come on, philosophically, if you, and I'm sure that you have a common sense, you will say, if I don't know the load with great accuracy, how in the world I can design the system? Okay? In reality, the columns never suddenly buckle. Instead, they begin to bend, also ever so slightly, immediately after application of the load. As a result, the actual criterion for load application should be limited either to a specific deflection of the column. Okay, so specific deflection of the column means this is stiffness. So what we are talking about, that there are various failure mechanisms suddenly come into play together. So designer wants either specified deflection of the column, or by not allowing the maximum stress in the column to exceed an allowable stress. What is allowable stress? I will just explain you. This allowable stress is a yield stress divided by factor of safety. We would like some safety from that value. Should not touch my face. So idea of factor of safety naturally comes to 17.8. Again, we have epsilon, sigma, and that is the straight behavior. So this is yield. Yield stress. Naturally, sigma yield is a dangerous level. So we should not reach it. So we can write down sigma must be smaller or equal than sigma yield. So, or we can put a flag here, like somewhere, which says don't approach cliff of sigma y, or cliff. So usually if there is a cliff here, that is here. That is dangerous. We are not allowing to get very close to the cliff. So there is this buffer zone. So this is some buffer zone. So then this is sigma allowable. So sigma allowable equals sigma yield divided by factor of safety. Okay? So this factor of safety is bigger than 1. And this is usually called also RFS, required factor of safety. The question is, of course, who requires? Society through codes. Okay, codes are, society requires that you comply with the codes. Okay, so that is this required factor of safety. In one of the particular cases, we had, I think, factor of safety 3, I think. Yeah. In previous case, we had required factor of safety equals 3. So that came from the code. Any questions? So if not, then so that is allowable stress. To study this effect, means of eccentricity, we will apply the load to the column at a short eccentric distance. It is not that we apply, so that is this, we will apply, it says. Better to say, we assume the realistic case to be that load is distanced. Okay, that is not that we apply, because if I have to apply, then I better apply in the center, then I don't have this problem. So realistic situation is that load is by itself displaced because there was manufacturing, etc. So that is the case. Look, please, that is a cross-section. This cross-section load is not applied at the center of cross-section, but is applied at some distance. Okay, E. Okay, then pay attention. Bending moment, we said, before eccentricity, in the very first lecture on buckling, we said bending moment, that is mz, equals minus p times v. So that is ideal. Minus p times v. That is ideal. Now we have, there is this v and there is e. So bending moment equals minus p e plus v. This is known. This is not yet. Then the differential equation was before EIV second derivative minus PV. Now it is minus PE plus V. Any questions? So there is this as if innocent. So pay attention. That is this is center line. Centroid is not here, but centroid is somewhere here. So that is this E. Any questions? No. We continue. So then we have second derivative of v with respect to x plus p over e. So that is, so we have ei d2v dx squared. Then this term I'm transferring on the left, plus pv equals minus pe. And then I divide everything by ei. So then I get second derivative of v with respect to x plus p divided by ei v minus pe ei. Now, this is ordinary differential equation, inhomogeneous, because there is left-hand side, right-hand side, sorry. And right-hand side does not depend on right side, does not depend on v, the unknown. You can say we can put v also on the right-hand side. No, because v is unknown. Unknowns, whatever is connected with unknowns, we put on the left-hand side so that we see what is known, what is not known. This is known, that is not known. Okay, now this differential equation can be solved. There is complementary solution and particular solution. So I will write down and I will give you this part in more detail. Seventeen 9. So we have d2v dx squared plus p over eiv. That equals minus p eie. Okay? Now, complementary solution. Is solution of associated homogeneous equation. And that is d2v dx squared plus p over ei v equals 0. Okay? Then we actually found already this. If you remember, we denoted this as k squared. And then we found v of x equaled c1 sine kx plus c2 cosine kx. But I will derive again. So look, please. V of x, we are here. We are looking at c times e in power rx. R is characteristic constant. Exponent. I substitute this there, will be c r squared, and then e in power rx. Then plus p over ei. Then will be c in power rx. This equals 0. Then I take c in power rx, outside parentheses, r squared plus p over ei. That equals 0. C is not 0. In power rx is not 0. So then r squared plus p over ei is 0. So that means that r squared equals minus p over ei. Oh, I'm squaring r and get something minus. Of course, Cardano would have hated this, calling it senseless. Okay, then R equals plus minus I square root of P over EI. Okay, so then V of X equals C1, okay, here, E in power plus I P over EIX plus C2E in power minus P over EIX. I put paper here. So then we get V of X equals C1. Now we are using Euler's formula. Cosine P over EI X plus I sine P over EIX. You know what? I will just make one change. That I will denote this, yeah, that is correct. I will, when I'm searching, I will not use C, but I will use D. Okay, so will be D, and here will be D, this will be D, and D is not 0, and D, and D. Because why always C? I like D also. I like C, I like D, and I like CDs. Okay, so we have here D1 plus D2. Here will be cosine P over EI. Minus I sine P over EIX. Now this equals, we take cosine here and cosine here. Cosine P over EIX. D1 plus D2. Then we have plus sine. Actually, we do differently. We take first the sine and sine here. Sine P over EI X. ID1 minus ID2 plus cosine P over EI X. D1 plus D2. This I'm calling C1, and this I'm calling C2. So then I get V of X equals, that is complementary, C1 sine P over EIX plus C2 cosine P over EIX. So I will just supply here complementary. Any questions? So I obtained this complementary. Now particular solution. For particular solution is any particular solution of the inhomogeneous equation. any one solution. Fable, I mean, connection with life. After French Revolution, the greats at French universities were given like this. If anyone could answer the question, likewise test, exam, whole class was passed. As you see, modern France is not using this system. Only after revolution, that is a method that was used. Here we want any solution, like here any student who answers the question. So 1711. So our equation is our equation is on top of page 683 or 17.8. So that is d2v dx squared plus p e I v. That equals minus p e I e. Now, we want to find any solution. So, look please. This is a constant. So, hence, idea comes, let us look for V particular as a constant. So, V particular will be not C, not D, let us say some A. Then I will substitute. I'm substituting this into here. Second derivative of A, dx squared, plus P over EI A equals minus P EI E. This is 0 because it's a constant. So from here I get A. A equals minus E, because that is this one and this one. Okay, so V particular then equals minus E. So then V of x equals V complementary plus V particular and equals C1 sine P over EI x plus C2 cosine P over EI x minus E. We will continue next time. Any questions? If you have any questions, please communicate to me. Have a wonderful day. Eleven, 8. 10, 9, 8. So that is your last lecture in FAU this time.
Yes. Let's see in the future.
Yes.